In this lecture, we're going to talk about the tensor character of stress. Now, I've left it as a take-home midterm problem for our class to show that stress is a second-order tensor. And in general, an nth-order tensor transforms according to this definition. The new components of a tensor that may have n different subscripts as an nth-order tensor, t sub p1, p2 through pn is equal to a p1, q1, a, p2, q2 through a, pn, qn, where a represents the transformation matrix, the matrix of the sets of direction cosines, times t, little t, q1, q2 through qn. Okay, there's a whole lot going on in this. Okay, so these are the subscripts on the tensor in the new coordinate system. The A's represent the transformation matrices. I have probably used M in the past, and I will use M again. And T with components, little t with components Q1, Q2 through Qn represent the tensor in the current coordinate system. Okay, so these are the components in the old system, and these are the components in the new system. Now, this thing that is a tensor can exist without a particular coordinate system being defined, but if you find its components in one system, it will transform according to these rules for components in the old and the new system. They're related this way. Now, what we're going to do in this lecture is we're going to talk about how this works out for stress as a second-order tensor. All right, so let's take a look. I'm going to represent capital sigma with a squiggle underneath of it as the new tensor for stress. And I'm going to represent the sigma as the current or the old stress tensor. And I'm going to use M as my transformation matrix. All right, let me make a little bit of room. Let's talk a little bit about this transformation matrix. We've done something similar for strain, so we'll move a little bit more quickly here, but just as a little bit of a refresher, our transformation matrix is constructed by looking at the components of the direction cosines from the old to the new coordinate system. So suppose I have a coordinate system sitting in space, and I'm just going to do this as a kind of a 2D picture this time. Z's coming out at us. We have a new coordinate system. That's going to be the capital X, the capital Y, and then the capital Z. Like that. And suppose we wanted to find one of our entries in our matrix. Okay, and let's put a little bit more on here, like maybe this is the angle from the x-axis, the little x, to the capital X-axis. we can write a vector that points in the capital X direction that's made up of little x and little y parts of it. Okay, so if this is a 2D type situation, the little z and capital Z line up on top of each other. In order to get to a direction that goes in the capital X direction, I would go over a certain amount in the x, and I would go up a certain amount in the little y. And if that's the angle theta, in the 2D case, this would be cosine theta, and this would be sine theta. So the capital X direction vector would be equal to cosine theta times the e hat one direction plus sine theta in the e hat two direction, and in this particular case 0 in the e hat three direction, because it's all lying in that particular plane. So the M12 component would be the dot product of this unit vector x that I've written here. It's important that we note that that needs to be a unit vector. Dotted with the e hat 2 basis vector. Okay, so in this particular case, that would be equal to what, sine of theta. And likewise, M11 would be equal to that x vector dotted with the e hat 1 direction. And I guess what I should really be careful about, I guess I should call this direction the capital E hat 1, and I can call this direction the capital E hat 2 direction, and that'll be kind of analogous to little e hat 1 and little e hat 2. Okay, so let me write this just slightly differently. Let me go ahead and change my notation here. I don't want my unit vectors to get confused with my x, y, and z axes. All right. And likewise, if we wanted to find find M13, it would be e hat 1 dotted with e hat 3. So in general, we can think of our components of Mij being equal to e hat I, capital E hat I, dotted with little e hat j. And this table that I'm setting up here has these components, M11, M12, M13, and so forth. Now, an important thing to note about this transformation matrix, you notice I'm not calling it a tensor. It is a matrix of components, and it is not necessarily symmetric. In fact, it usually isn't symmetric. So M12 may not be the same as M21. So it's going to be important that we kind of keep that in mind as we do these manipulations. And the reason why those aren't necessarily the same is we can take a look at E hat 2. Let's go ahead and write down what E hat 2 is equal to. This is the same angle theta. I would go in the minus x direction, the minus E hat 1 direction. I would go minus sine theta, cosine theta. in the E hat 1 direction, and I would go plus. No, I had it right the first time. I would go minus sine theta in the E hat 1 direction. And I would go up positive cosine theta in the E hat 2 direction. And then 0 in the E hat 3. So M21 would be equal to capital E hat 2 dotted with little E hat 1. Okay, and that would be equal to minus sine theta. Okay, so we see here a specific example in which M12 is not equal to M21. Again, it's really important that all these things that we're dealing with are unit vectors. Let's go ahead and write down what capital E hat 1, 2, and 3 are for this particular case. So in the two-dimensional case, we can write down these sets of unit vectors in the capital XYZ system, from which we can find our matrix of M's or A's. Sometimes the book uses the A and I use the M. Cosine theta, sine theta 0, minus sine theta, cosine theta 0, 0, 0, 1. Then for a second order tensor, the components transform according to this equation. Capital sigma ij, that's the components in the new system, transform like sigma kl, the lowercase sigma, mik, mjl. Now some people write the transformation matrices in front, so we can do it this way: mik, mjl, sigma kl. Now, since I've also been trying to emphasize the matrix nature of all these calculations, and I think in a lot of cases when you have all these numbers, it makes things a little bit easier if you deal with the matrices. Another way to think of this is the components of the new stress tensor capital sigma can be found by looking at M with a squiggle denoting a matrix, sigma, little sigma, the current components, times M transpose. Okay, so you pre-multiply with the M and you post-multiply with M transpose. Let's go ahead and do that in this case. I'm going to write down all these matrices that we have here. Now you can do this in the general three-dimensional case. I'm doing this in the two-dimensional case. So there's my M matrix. And suppose I have a state of plane stress where I have components in the plane sigma x, sigma y, and tau xy. I could even have a sigma z for what's called generalized plane stress. And now I'm going to post-multiply it by the transpose of the matrix M. Alright, let's go ahead and do this multiplication. I'm going to multiply the back two matrices first. So now I'm just copying down this current matrix of components. I'm going to take this row, cosine theta minus sine theta 0, multiplied by, I'm going to take this column, cosine theta sine theta 0, multiplied by this row, sigma x tau xy, and 0. So I'm going to have sigma x cosine theta plus tau xy sine theta plus 0. I'm going to write that down. The next one, I'm going to take this column and multiply it by the next row. So I'm going to have a tau xy cosine theta plus sigma y sine theta, and then this last one will give me 0. Okay, now when I multiply two matrices together, I get a matrix. I'm putting a dash here to kind of separate this out so it's easier to see. These matrices have a lot of terms in them. I'm going to take this column, multiply it by the top row. I'm going to have a minus sigma x sine theta plus a tau xy cosine theta. I'm going to take this row times the second, this column times the second row. I'm going to have a minus tau xy sine theta plus sigma y cosine theta. And then on my last term I'll have 0. And finally I'm going to take the last column and multiply it by each of the rows. This one's going to be real easy. The first entry is 0, 0 times sigma x, 0 times tau xy, and 1 times 0. The next entry is 0, and then the last entry is sigma z. Finally, I'm going to take these two matrices and multiply them together. I'll take this column multiplied by this row. That's going to be the result, capital sigma 1, 1 component. It's going to be a sigma x cosine squared theta plus a tau xy sine squared theta. Sine theta times cosine theta, getting on the wrong row. So this entire term times the cosine theta. Now I'm going to have this entire term times the sine theta. So I'm going to have a tau xy cosine theta times a sine theta, and I'm going to have a sigma y sine squared theta. All right, continuing on, I can write down the term capital sigma 1, 2. All right, it's going to be this row, this column. I've been mixing that up. This column times the second row over here. So the first term, I'm going to have a minus sine theta multiplied by all the terms. So let me write this as a minus sigma x sine theta cosine theta minus tau xy sine squared theta plus tau xy cosine squared theta plus sigma y sine theta cosine theta. The result of the next one, sigma 1, 3 would be equal to 0. Okay. Sigma 2, 1 is the same as sigma 1, 2 because the stress tensor is symmetric. The next one that is unique is capital sigma 1, 2. That's going to be sigma x sine squared theta minus tau xy sine theta cosine theta minus tau xy sine theta cosine theta plus sigma y cosine squared theta. And then the last one, unique one, then will be capital sigma 3, 3, which will be the same as sigma z. Okay, so these are the unique components of the stress transformation based on plane stress, or generalized plane stress, and an in-plane rotation. Let's make a little note of that. Okay, now in general you can do this in general three-dimensional transformations, and in that case it's handy to have MATLAB or a computer program of some sort in order to do these particular matrix calculations. But I wanted to show what these equations look like. Now we're going to do a little bit of manipulation on these. Let me make a little bit of room. Okay, we can note some trig identities. For example, 2 sine theta cosine theta is equal to sine 2 theta. Sine squared theta is equal to 1 minus cosine 2 theta over 2, and cosine squared theta is equal to 1 plus cosine 2 theta over 2. So with those identities in mind, we can rewrite these in terms of the 2 theta formula. Capital sigma 1, 1 is a sigma x over 2, 1 plus cosine 2 theta plus sigma y over 2, 1 minus cosine 2 theta plus tau xy sine 2 theta. Capital sigma 2, 2 is sigma x over 2, 1 minus cosine 2 theta plus sigma y over 2, 1 plus cosine 2 theta minus tau xy sine 2 theta. Capital sigma 1, 2 is equal minus quantity sigma x minus sigma y over 2 sine 2 theta, and then a plus tau xy cosine 2 theta. Alright, I'm going to write these one more time where I'm grouping the similar terms, like the sigma x over 2 times 1 and the sigma y over 2 times 1, and then so forth. So let me write these one more time. And we have these terms. Now, in undergraduate mechanics materials, when I teach this class, when I teach this subject in that class, plane stress transformations, I usually call this sigma x prime. I call this sigma y prime. I call this tau x prime y prime. These being the stress components in the new coordinate system. Now, we know some things about tensors. One of the invariants of the stress tensor is that the trace of the stress tensor has to remain the same no matter what your coordinate system is. So let's check this. Let's compute our first invariant of the stress tensor. I1, the new terms are capital sigma 1, 1, capital sigma 2, 2, plus capital sigma 3, 3. If we look at this first two equations, the second two terms in each of those equations annihilate each other when we add them, and we have sigma x plus sigma y over 2 plus sigma x plus sigma y over 2, and then we have sigma z or sigma z. Let's just write that with one subscript. And we do indeed when we add these together, we get sigma x plus sigma y plus sigma z. And if we add up the components in the previous coordinate system, well, that's just the three diagonal components, sigma x plus sigma y plus sigma z. And these do match, and that is invariant under coordinate transformation. Well, the other thing that we can do with this is we can talk about something called Moore's circle for stress. Moore's circle for stress isn't necessarily just for stress. Moore's circle can be applied to any tensor that can be kind of degenerated into something that looks like a matrix for generalized plane stress. In other words, we can have the three diagonal components, and we can have one off-diagonal component, the other terms being 0. That'll be the main topic of the next lecture, but let me save this page and kind of show this situation here, where we have a matrix that looks like this, symmetric, Moore's circle will apply to any second order symmetric tensor that has zeros in those places that I show here, or somehow you can rearrange it to have those zeros in at least two planes. Right. So the next lecture will focus on how we get to Moore's circle from the plane stress transformation equations, and I'll try to do an example, maybe do one with some numbers in it so that we have something to look at. We'll also compare that to our interpretation of the eigenvalue problem.